Welcome to 13th seminar in the Indus Seminar series. Today's speaker is Arpit Shrivastav. Arpit is a final year PhD student at Aries Nainital and IISc Bangalore. He joined the Joint Astronomy program at IISc in 2019 and later moved to Aries Nainital to work with Professor Deepankar Banerjee and the Solar Group at Aries. He recently submitted his thesis on the observational study of Decayless waves across various scales in the solar corona and will present a similar topic in this talk. His research includes statistical analysis combining observations from different sun regions using solar orbiter. Arpit, you may start.
Okay. First, thank you, Gauri, for this nice introduction. And I would also like to thank Indus for providing me the opportunity to present my work here. So, yeah, I'm Arpit Shrivastav. I'm a PhD student with different people from ROB, KV Livian, and I would also like to thank them for providing valuable suggestion on this work. So let's start. So, 1 second. Yeah. So when we look at the solar corona in EVs, we see several open closed structures like this, like shown here in this image, and mode in these structures. So in sausage modes, you will have uh, a perturbation which is symmetric to magnetic axis of the magnetic cylinder or magnetic flux tube. While there could be other wave modes like kink mode, in which you will see a bulk movement of the cylinder or magnetic flux tube, and the magnetic axis of the flux tube is disturbed. Apart from that, there could be other wave modes like torsional alternate waves and floating wave modes, which can affect the geometry of the flux tube in a different way. Uh, Other than the wave modes which can affect the geometry, there could be wave modes which can also uh, in which there can be intensity oscillation along the loops, and uh, these are known as slow mode waves. Can you please confirm I'm audible and visible as well?
Yes, and
Yes,
yes.
yes, you are. Yeah.
Okay, thanks. So in this talk, I will mainly present in this just the uh, just the intensity along these lines, and we extract this intensity to get the characteristic of these oscillations. Now, ca- these kink modes can be divided into different regimes, and depending on what kind of wave characteristic we are able to see in the solar corona. And the main regimes are standing and propagating. So, in standing regime also we have different categories like decaying oscillation, in which the amplitude of the oscillation decay with time in several cycles, in a few cycles. And there could be decayless oscillation, in which the oscillation does not decay with time, and oscillation amplitude does not decay with time. These are excited by different drivers, which and decayless oscillation, I will explain more about them. Now, there could be propagating kink waves, which has been observed in Doppler velocity time series of comp data, and they are interpreted as these intensity fluctuation which you see in this animation are interpreted as propagating kink waves. In standing kink waves, there are other characteristics as well. Like if we look at the phase lag between different oscillation at different position of the loop, like here you will see one, two, three. There are three slits, and at in which the oscillation are found in kink for kink mode, and almost there is no phase lag for standing kink oscillation, which is natural. So the one important aspect of kink oscillation is I also said that there could be decay coronal eruptions. They are not excited by these kind of mechanisms, and they have average period and Finogentop et al. have been observed these oscillation in large loops, and they have measured the period of these oscillation where the average period is around 251, as you can see in this distribution. Which indicate that these are standing in nature. The Decayless oscillation are standing in nature. This standing nature can be understood by the fact that if you assume a fundamental standing mode going on in these loops, the phase speed of this fundamental standing wave will be 12 by p, and in the thin flux tube limit, this vph can be approximated as ck, and this ck is kink speed, and this kink speed is also can also be uh, interpreted from this formula in which we have uh, a square root of magnetic field and density. So if we assume that magnetic field and density is not varying much in the corona, then you can assume that there is a linear relationship between L and P, because Ck is proportional to Vp. Ck is equal to Vph in this particular limit, and P will be proportional to L if Ck is almost constant. These Decayless oscillations are ubiquitous feature in solar corona, and that's why they are important in coronal heating as well, because of their common occurrence in solar active regions, and in the solar corona in general. Now, as their amplitude does not decay with time, there are different phenomena, different interpretation has been given how these are excited and sustained for a long time. So uh, there could be different drivers which can give rise to this oscillation or sustain these oscillation, like harmonic foot point driver, random foot point motions, and these proposed driver were not able to provide the observational characteristic of these oscillation which we see in solar corona. So in 2016, Nakarika have given an interpretation that there could be interaction of loop with Cauchy steady flow, and Cauchy steady flow can be interpreted as supergranular motion, and this particular mechanism can provide the energy to loop such that it counteract the decay mechanism. So this particular figure dictate that scenario by a mechanical analog of conveyor belt and a spring mass system. But recently, Mondal et al. Found that by in their observation that these kink oscillation, decreased kink oscillations, in their observation they found that there is no evidence of commonly suspected sources, and this makes the drivers of Decayless oscillation highly debatable. So there is not so much consensus about their driving mechanism as well. Another important aspect of these oscillation is coronal seismology through Decayless waves, and so in observation we have oscillation characteristics such as wave properties such as amplitude period. We can estimate the physical parameters such as density and density contrast from observation as well. And then using MHD wave theory, we can estimate the magnetic field. And um, all these steps are combined and can be known as quantum seismology. So from MHD wave theory, we get this formula of magnetic field estimation, and in which loop length, period, density, and density contrast are there. And by calculating these values, we can estimate the field of value of magnetic field. Now, this particular method has been for magnetic field in small scale loop in different regions. So although there has been few attempts for decayless oscillation in small loops in quiet sun using AI data as well. So Gao et al. Has studied around 16 loops and found 31 decayless oscillation in coronal bright points in quiet sun region. And as you can see, they have to use motion magnification mechanism, magnification algorithm actually, to find the oscillation in the small scale loop, because AIA does not has sufficient resolution to resolve these oscillations. Now, the energy in these Decayless oscillation in small scale coronal bright points, they concluded that it is not enough to hit the energy needed to hit the quiet sun. Later, by using HRI UV data, Petrova et al. Has calculated had detected the oscillation Decayless. Here it is UV HRI UV observation, while Gao et al. Has utilized AI observation, which has guidance of 12 seconds. So, but in Petrova et al., they have studied only two loops, and it is not a statistical study, so we cannot say in general that that has been followed. The energy in general in these small scale loops, the Decayless oscillation energy flux is large always. Now in active region also there has been some attempts. So you can see here the efforts from Li and Long, in which they have studied around 111 oscillation in small scale loops in ARs in active regions, and they found that there are many short period oscillation which can provide high energy flux. But even though they find many enough to hit the active region. Now, if you look at the scenario of Decayless oscillation in small scale loops in different region, we have active region 111 oscillation from Li and Long. We have 33 oscillation from Gao and Petrova et al. In quiet sun, but we don't have any detection of Decayless oscillation in coronal holes. And if we want to understand how much energy they provide to corona, and if we want to understand what are their characteristics and their driving mechanism in different regions, we need more statistics in these regions as well. So with these background story, the motivation of our study is to understand what are the properties of Decayless waves in different regions, so that we can get a guess of their driving mechanism. Then, as I showed earlier, that they are standing in nature in large scale loops, but we don't know what is the nature of wave modes in the small scale loop in of Decayless oscillations. Also, one of the important factor is how much they contribute to coronal heating. So as you can see in this right plot, this loop length versus oscillating period relation, if that is follow for smaller length as well, we expect that there will be short period oscillation in at smaller lengths. And if we assume there will be a short period oscillation, then there will be high energy flux for corona. And that's why they are important in coronal heating as well. So we want to know how much contribution of these Decayless waves is there in different region of the sun. And we also want to estimate the magnetic fields in the short loops using coronal seismology. So these are all the motivation. And what do we need for analyzing this kind of, or answering these kind of questions? We need high resolution observations, which has not been present in previous years. And now we have high resolution observation from solar orbiter. So solar orbiter has 6 remote sensing and 4 in situ measurements instruments. And one of the remote sensing instrument is extreme ultraviolet imager EY. It has 3 telescopes, one full sun imager, and two high resolution imager in EUV and extreme ultraviolet and limonal. So these animations show different 3 different telescopes and their time series. So you can see the HRI UV. You are able to changes in physical units, and it can go up to 100 kilometer at near the perihelion. So, to study the small scale loops in quite some coronal holes, we utilize the 3 datasets from solar orbiter. The characteristics of these datasets are shown here, and you can see the plate scale of these datasets around 100 to 200 kilometer, and cadence is around 3 to 5 seconds. So these characteristics are very important to observe the small scale loops, and if we want to find any high frequency oscillation in them, so that we can get the high energy flux. Now this animation are depicting the 3 dataset or 3 different time series we took. And if you see, there is nothing happening no activities happening in these animations. But if we go to smaller scale, if you zoom in these images, then you will see that the dynamics of the small scale loop is captured by the HRI-UV telescope or HRI-UV images. Now, these dynamics were not clearly seen by EIA earlier. And to analyze the oscillation in these small scale loops, we have aligned these images. And so after aligning these images, we have picked up different small scale loops. And if you want to if you want to get the oscillation in them, we have put this artificial slit to detect the oscillation in these small scale loops. You can see from this animation 3 examples of these oscillations. So these artificial slits will be used to make the XT maps, which is the time series of the intensity along these artificial slits. And we see different signature of oscillation in these XT maps. So these are the targets which we analyze. And uh, we we estimated amplitude and period of these oscillations. So from the XT map, we fitted the loop positions at different times by a sinusoidal function provided here. And we found the period amplitude assume that the the loop are following Semus-Alcorn model. And we just measured the points where the loop foot points are embedded. And using this formula, you can get the loop length. Now after doing this for 42 oscillations, we have made a histogram of these oscillations. And we found that the loop length average loop length is around 9.1 megameter, which is smallest for any statistical study done so far. And we found these are the range of parameter we found. We found the period between 30 to 26 seconds. So there are, as you can see from this distribution, there are uh, many short period oscillation, but also from this distribution, it is visible that there are many long period oscillation as well. But if you compare this distribution to Gao et al., who studied using AIA, also we did the analysis for coronal hole and Quetzalcoatl loop, although Gao et al. Has only done it for Quetzalcoatl coronal breakpoints, and we find many long period oscillation compared to short period in these small scale loops. Now, the other thing is what is the wave mode of these loops, these oscillation in the small scale loops. So, as you if you remember that the large loops follow the correlation, the large loop follow a linear relationship between loop length and period, but in our study we didn't find any correlation between loop length and period, and that is surprising actually. What could be the reasons? So are these is this no correlation indicates that there is no signature of standing waves? Plot all these oscillations, small scale and large scale, Decayless oscillation in small scale and large scale. If you plot that in one figure, so here I have combined all the oscillation from previous works and including our one in red color, and you see for large scale loops there is a linear relation which can also be seen in this plot. But from small scale loop, you see a different branch that is emerging, and this second branch is quite interesting. This has implication of wave mode as well, which I will explain later. But if you want to understand the scenario of underestimation of loop length, you will see here that even if I underestimate the loop length by 20 megameter in these small scale loops of 10 megameter, then also this branch will not shift, that it will align with the case of large scale loops. So it could not be underestimation of loop length. So it can be that these waves are not standing, but we will see that in the next slide. Now we also calculated the correlation coefficient for loop length and period for only Poisson loops using previous studies, and we found that the correlation coefficient is 0.47. But still, it's not sufficient to say something confidently. That's why we cannot say right now that these are in line with standing wave signatures. Now, even though we don't have any correlation between loop length and period, we can estimate the nature of these wave modes by measurement of phase lag by measuring the phase lag at different location at the oscillation profile at different locations of the loop. So here you can see I have placed the slit at different position of the loop, and we have found the oscillation in them. And if you see the phase lag between these oscillations, there is no phase lag actually. So what does that indicate? That indicate that these are standing kink waves. But there is one problem here, that these slits are not very wide, because these loops are very dynamic. We cannot find any oscillation signature at the loop foot point, and that's why we have to put the slit close to the loop top, and and that's why we cannot confidently say here also that these are standing waves, although the no phase significant phase lag is obtained, and this can indicate standing mode, but we are suspicious also here. So what could be other possibilities that we can understand from here? So let's understand other possibilities. So if you want to let's suppose a scenario of propagating kink wave. So if you take a propagating kink wave with a kink speed of 1,000 km/s, then to get a significant phase lag, and to say that it is a propagating kink wave, we have to put the slit several megameter apart. If you put the slit several megameter apart, then you will be putting the slits at the distances which are which are which are close to loop length, or half of the loop length. And in that scenario, we will not able to I mean, as I said, these loops are dynamic, and there is no signature of waves as we go towards the foot points. That's why it's difficult to detect the reverting kink wave signatures using the cadence we have, because in 3 or 5 second cadence, this propagating kink wave, if it is there in these loops, it will pass these two slits, and we will not able to get significant phase lag for that propagating kink wave. So it's difficult to get the signature of propagating kink wave, in my opinion. And there are several other possibilities which were recently explained in a simulation by Gao et al., in which he have simulated a small scale loop, and he have simulated Decayless oscillation in small scale loop, and they found that these loops have there are two type of oscillation that has been excited in these small scale loops. And one type of oscillation is close to kink mode period, or natural fundamental mode period, which is very short, and one oscillation period is close to the period of driver they have used. And that's why this particular simulation also provides an explanation to our oscillations. And long period oscillation, which has been detected in our study, could also be manifestation of the period of driver. And they have used a driver which has period close to 300 seconds. That's why they got a long period oscillation in these small scale loops. Now, if we talk about the estimation of magnetic field, so the range of magnetic field we got around is 0.35 to 8 Gauss, which is quite typical, which can be quite close to Poisson coronal hole magnetic field. And the energy flux of these waves does not seem enough to hit the Poisson and coronal hole region. So this was the story of Poisson coronal hole loops. Uh, but we didn't find as much high frequency oscillations. And as there was in active region Lien long analysis. And although there are few high frequency oscillations are present, they may not be prevalent in these regions. So in quite some we found these interesting results. But what about in inactive regions? So as we found a secondary branch in quite some, do we have do we see that kind of branch in active region as well? So this question will always remain. So to understand that, let's revisit the air short loops, their behavior, which was previously studied by Lee and Long. So you see here, they studied short loop of around 15 megameter length, and they found a good correlation between period and loop length. That is very tight correlation. So that is very different from what we found in quartz and coronal hole loops. So why is that? I mean, what the reason there is drastic difference in the results of these two analysis? So there could be one limitation of Lee and Long, which has been which could affect this period versus loop length correlation. The They have not included any oscillation with period greater than 200 seconds, and that could affect this correlation coefficient. And they have not provided any reason as well. So what we did, we tried to analyze the active region loops, short loops again, with solar orbiter datasets of two different active regions. And as you can see here, I think animation is playing. Oh, okay, it's slow, I think. Okay, so these are the artificial slits we took in small scale loop in different regions. And these are the specifications of those data sets. You can see also here that the plate scale is quite good, and cadence is around 3 seconds, which is very good for capturing high frequency oscillations. Now, the analysis is similar to quartz and coronal hole loop, so coronal hole oscillation. So that's I will not gonna repeat that. We studied around 130 oscillation in these small scale loops in active regions, and the natural step will be to make a histogram. So you see these small scale loops in AR, they have average length of 19 megameter, which we studied, and they have average period of 162 seconds. If you compare this histogram with quartz and coronal hole loops, you will see that the average values are quite similar, even though the length is a length in AR small scale loops is twice larger than quartz and coronal hole loops. So what does this indicate? I mean, why there are similar properties of oscillation we are getting in different regions? To understand that, we make a combined plot of period in quartz and coronal hole and active regions. So in this plot, the cyan one is for active region, and the this pink one is for quartz and coronal hole, and we see that for longer periods there is not much difference, but for smaller period we see a larger difference. And what does this larger difference indicate? So this also indicate that there could be different driving mechanism in this particular regime of shorter period in quartz and coronal hole and active region. In those two different regions, there could be difference in driving mechanism, and that's why there is a high number of high frequency oscillation in active region, while there are low number of high frequency oscillation in quartz and coronal hole. But you should note that in coils and coronal hole, the 31 oscillation from Lien Long, sorry, from Gao et al., and they have used EIA data. So it is also possible that in coils and coronal hole, we are not able to detect many high frequency oscillation because of the imaging cadence of the data set we have used. Now, again, the story for loop length and versus period, we didn't find, again, no correlation for activity in small scale loops as well in the period and loop length. And we did find the secondary branch in active region as well. This also marks the similarity between Decayless oscillation in different region on the sun, and this second branch is also present in active regions. Now, again, we did the similar analysis for activation loops, and we found there is no phase lag, which kind of indicate standing mode. But as I said, there are different possibilities for these wave modes. One possibility is that there is no phase lag; they can be standing waves. But even though there is no phase lag, there is no correlation between loop oscillation is dependent on the driver period. It will not be reflected in it will not be governed by I mean the fundamental kink mode, and then there will be no correlation. But they did find the simultaneous long and short period oscillation, which we didn't find in our observation. So that's a one thing which we can explore later. Also, there is a possibility that these loops may have chromospheric or transition density. If they have larger density, the kink speed can be lower in that case, and and the period which is depend on density as well will be longer. But we don't know because we only have observation from coronal regions and not in chromospheric and transition regions. And there can be a possibility of propagating kink wave, which may not be detected due to instrument limitations. This explains no correlation between loop length and period, because the properties will be also be dependent on the driver for propagating kink waves. But we don't know because we have instrument limitation in this case. So there's kind of different possibilities which governs which can explain these oscillations, and that's why we are very uncertain about the wave modes. Now again, the coronal seismology part, in this we found that in active region, the range of magnetic field is around 0.2 to 32 Gauss. So there are around, this coronal seismology has been applied for large scale active region loops as well. And the range is, for those loops, is around few Gauss to few tens of Gauss. But in our study, we found that 25% of oscillation has magnetic field less than 2 Gauss, and there are around 10 to 12 oscillation with long period. They have magnetic field value of less than 1 Gauss, and that is surprising because in active. Also, if these waves are driven by some driver, so oscillation period will not be dependent on loop properties, which will be in the case of standing mode. And in that case, we cannot apply the formula of coronal seismology as well, or the density of these loops are higher, and in that case the magnetic field could go up in that case. And we don't know the densities, if the densities are higher or not. We have only assumed, we have only utilized the density of corona in these coronal loops to estimate the magnetic field. So in conclusion, this coronal seismology technique should be used with caution for these small scale loops. As there are many possibilities, we also try to find out whether there can be any factor which can distinguish the properties, or the different wave modes which can be uh, if you take all the oscillation which has value greater than one particular kink speed, that define the kink speed cutoff, and you vary this cutoff from 0 to 600 kilometer per second, which I did for this plot. And what we found was, after the after kink speed cutoff of 400 kilometer per second, we have correlation coefficient of loop length versus period greater than 0.7, which is similar to what Infinogentov has find. Infinogentov et al. Has been found, has found in large scale loops. And that's why it indicate that if we have higher kink speed, there could be possibility that those mixture of wave modes. And so that's why the kink speed can be connect as one distinguishing factor. And in conclusion, there are mixture of wave modes. That's why it's difficult to get the magnetic field, and that's why there are many possibilities which complicate the situation. So in summary, in different coronal region, we found that there are more high frequency waves in active regions, while there are less high frequency waves in quite some coronal hole. And that's the difference we found in different coronal region of the sun for decay's oscillation. And there is presence of secondary branch in active regions as well as in coronal hole and quiet sun. So about the wave modes, these are the wave modes are uncertain, and there are several possibilities. That's why the wave mode are uncertain. And due to instrument limitation, also we are not able to clarify that. In the context of coronal heating, they have low energy flux, uh, tell in a much better statement whether they are important for coronal heating or not. From magnetic field estimation from coronal seismology, we found that we have to use this technique with caution in the short loops. what we can do further in terms of wave mode, we can use multi-wavelength spectroscopic observation from different spectrographs such as ice and iris, and we could estimate the densities. We could try to find out if there are signature of other wave modes or not. So that's the future step we can take for detecting the oscillation in the small scale loop um, in transition region simultaneous observations. There could be other exploration of these loops in using future high cadence imaging observation of UI, which may be available in few months, and in future hi
Thank you,
Gauri.
Arpit, for a wonderful talk. So do we have any questions? We have a question in chat box. How did you estimate the
Yeah,
loop length?
yeah. So, I mean, we have assumed here that the loops are semicircular, but they can be elliptical as well. So, if you assume the loops are semicircular, then you just have to estimate the 2 foot points, and then you have baseline, and from that you can estimate the loop length using the formula of L equal to phi pi r. Just simple as that. Yeah, so there is one question from Yogesh, Gauri.
Yeah,
Yeah,
so
so
Yogesh is asking what is the highest frequency we can observe from remote sensing observations?
so uh, currently we have observation from solar orbiter which has cadence of 3 seconds. So if you assume if you take the 3 second cadence, so considering the Nyquist frequency, we can at least observe 6 second oscillations. But still, we have till now we have only observed till 12, 11 or 12 second oscillation in remote sensing observation. But in principle, we can observe of 6 second as well, I think.
Ashwin is asking, could you please let me know how you get to isolate and identify the short loop structures for this work?
Uh, I mean, you don't have to uh, isolate it because it's a high resolution observation. So you can see them in animation, and then you can target whether loop structure is well visible or not. And then if you target them, and then you place the slit, you will able to get the oscillation in them. So it's not like if the loop has several strands, we will not able to distinguish that. That's a limitation of this study. But still, if the loop is sufficiently visible in the chronographic, I mean in these images or time series, we will able to analyze them actually.
Yes, since short loop structures are hard to found, uh, he was curious how to isolate it.
Okay.
Does anyone else have any question? You can ask directly by raising hand or unmute
Yeah.
yourselves.
Yeah, I have one question. Yeah, can I go ahead, Gauri?
Yeah, sure.
Yeah. Yeah, hi, Arpit. Nice talk. So
Yeah.
I was just curious regarding this wave observation, though it's not my field, as you know. So
Yeah.
how do you distinguish between different type of waves from just one observation? For example, slow and fast waves. Is it possible to do that?
Yeah. 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 So it's possible depend on the phase speed. So suppose you have kink oscillation. So if you calculate the phase speed and those phase speed are close to Alban speed or which is around 1,000 kilometer per second. So if they're close to those speed, you will say you can say that these are fast kink modes. Now, in the case of slow waves, their speed will be close to sound speed, and in that case, you can tell that it could be slow modes.
Okay, but that effectively, that plasma blob or that particular area will be the summation of all these things, right? So, how you identify the individual component?
Okay, so simultaneous observation of different wave mode is quite rare actually, Pratik. So, like if in the coronal loop, which we find um, kink mode, they are there for few minutes, I think, few oscillation cycles, and at the same time we may not find other wave modes. So there are few observation in which we found in which people have found simultaneous kink and sausage waves. So sausage wave will produce as you have seen in my talk, sausage will produce the continuous or periodic contraction and expansion of the loop, and that can be identified in imaging observation by measuring the width of the loop and separately, and then in kink mode it will be bulk movement, so it can be separated from sausage wave in the extreme map as well. So in that way it can be done, but in my opinion we do not see always the simultaneous presence of different wave modes, because they are excited by different drivers as well.
Yeah. Okay. Yeah. Thank you, Arpit.
Yeah.
We don't have any more questions. We can stop here. Thank you, Arpit, once again.
Okay, thank you.
Yeah, maybe we can give a big applause for the speaker. Today's speaker. Yeah. Thank you, Arpit,
Thank
and
you. Thank you so
thank you
much.
everyone for joining. Thank you so much.
Okay.